Now that you have a pretty good idea about the anatomy of the ocean floor, we can actually get into detail of the types of plate boundaries and the features that form them. So, divergent plate boundaries move apart, convergent moves together, and transforms slide against each other. But we're going to focus more in depth on why they occur and what features we can find. So let's get started. Divergent plate boundaries actually go through somewhat of a process over time, and that starts with the asthenosphere pushing up a lot of magma to the surface. And what that's going to cause is some sort of a deformation in the surface. So it's going to kind of push this oceanic crust upward, or continental crust in the case of Africa, actually. Okay, so it's going to push this up, which is obviously going to lead to a lot of volcanic activity as there's hot magma all over the place. And some forces that we're going to talk about later is essentially going to push this crust in opposite directions. So here are the steps that I'm talking about. Step one is the formation of a rift valley. And the rift valley is just this slightly heightened section of land caused by the upwelling of magma. Step two is when these plates actually move all the way apart, forming a sea, because this is going to move up and essentially form oceanic crust. That oceanic crust is going to lead the way for more ocean to form. So tectonic forces are going to push the plates apart, leading to emerging rift valleys, and then a sea eventually develops. And finally, after a long time, an oceanic ridge system like the mid-ocean ridge is actually going to form with that. So like I said, rift valleys are caused by this upwelling magma that pushes the land up. An example that I'd like you to be familiar with is the East African Rift Valley. You can look up the picture on your own time. It's actually worth checking out. Also, like I said, when these plates move apart, that magma comes up and new oceanic crust forms that is actually going to just spread apart. And this guy, Harry Hess, very, very smart man, Mr. Princeton and Yale over here, he coined the term seafloor spreading. And that's basically an explanation of what is happening with Wegener's continental drift. So we're going to get into that, but before I do, I want to talk about some more evidence for continental drift that we can now understand with the concept of divergent plate boundaries, and that is paleomagnetism. That's essentially the study of rocks and their magnetic properties, and if these rocks have magnetic materials like magnetite, it records the intensity or the strength and the direction of Earth's magnetic poles over time. So you can see how useful this is going to be. Over a long period of time, these rocks are going to move apart and they're actually going to point in a different direction. Okay, so they're pointing in all these different directions, which is extremely odd because, as far as I'm concerned, we only have one North Pole and one South Pole. Now, the actual physical location where the pole is slightly different from where all the rocks point at. And there are reasons for this, but I can't get too much in depth with that right now. However, you need to understand that these rocks are moving all apart and they face different directions, which is really, really odd, unless you take Wegener's idea of continental drift into account. So, remember that Wegener said, hey, everything's formed from Pangea. Everything started from this giant landmass, and everything spread apart through continental drift. So, if that were the case, we can actually take all of these different directions and put them together in one jigsaw puzzle, I guess, one supercontinent, Pangea, and they will end up pointing at the exact same location. That is paleomagnetism at work, and basically all these rocks are moving apart in predictable ways. So, young rocks are going to align perfectly with where the magnetic pole is today. But older rocks, the older you get, the more varied their directions become. And again, this is because of seafloor spreading, that sea moving apart, and that's basically continental drift. So all of this is going to be evidence of Wegener's continental drift. Okay, so I have a practice problem just to show you the extent of seafloor spreading and what that actually does. So remember, seafloor spreading was Harry Hess's term, and he basically said that, yeah, continental drift does occur, but that's because of something called a spreading center right here. Let me do this in different colors. So this magma rises, and forces, which I'm going to tell you eventually is convection currents are going to push this apart. And because they go in different directions, more crust is formed at the surface, more young, fresh crust, where all this other crust go in separate directions. All right, so that is seafloor spreading, where the sea is spreading because of that magma. So here's a problem that I want us to do together. It says this diagram below represents the pattern of normal and reverse polarity. So before I get too much into this, you have to understand that about every 500,000 years, give or take probably a lot, the North and the South poles actually just completely flip. I have absolutely no idea what that is or why that is. And I've always thought that was really, really cool. But basically what happens is you have this magnetic intensity with the North and the South poles, but eventually they start deteriorating just a little bit and then they switch off completely before you have a reversal. And the magnetic North Pole is actually the South Pole, and the magnetic South Pole is the North Pole, all that good stuff. It's really cool. But every 500,000 years, you're going to have a predictable direction. You're going to have a direction that these magnetic materials are going to face in the rocks. And basically, what ends up happening is those magnetic properties get locked. They actually go past something called the Curie point, which is the temperature at which magnetization occurs. Okay, and they're going to face a certain direction. So rocks are going to, again, have a direction recorded with them. And every 500,000 years, that direction switches. So you can obviously see the use in tracking these over time. I should have clarified this before reading, but represents the pattern of normal and reversed polarity and the relative age of the igneous bedrock composing the ocean floor on the east side of the mid-Atlantic ridge. The polarity of the bedrock on the west side is deliberately left blank. So the question is asking us to find out what that is on the west side. West side. It's been a long day for me. All right, so as our age increases, you have to understand that the magnetic polarity is going to switch. So this one is going to have normal polarity, but then eventually it's going to spread out. New crust is going to form, and that crust is probably going to go through a reverse polarity phase. Okay, so basically they switch on and off and on and off about every 500,000 years. Well, let's go back up to this picture right here. Convection currents are going to go in both directions. Okay, so they're going to go right and they're going to go left. So if seafloor spreading is occurring, that is spreading at a symmetrical pattern on both sides of the mid-ocean ridge. Okay, so we are looking for a diagram that is symmetric to this one. Okay, so if this has normal polarity, then crust on this side has to also have normal polarity. If this has reversed and it looks like it's pretty big, then this is going to be a pretty big reverse polarity as well. So that would make the correct answer A. Okay, because it is symmetric, and that is how seafloor spreading works. Another note about divergent plate boundaries, new crust is generated at a mid-ocean ridge. Also called a spreading center sometimes, because that's where spreading takes place. Okay, and the why, the most accepted mechanism is convection currents. So there are three types of energy transfers. There's radiation, convection, and conduction. But convection is basically wherever heat rises. Okay, hot particles move up and they bounce in different directions, and they are going to rise upward. And as they cool down, they are going to sink, and they follow some sort of a circular pattern. Well, if you have heat on the left and the right side that are both trying to come up, they are essentially going to push. So imagine something right here. They are going to push this crust in opposite directions. That's kind of the basic idea for convection. And I do want to note, there are other explanations for why divergent plate boundaries exist, why seafloor spreading takes place. Okay, they are ridge push and slab pull. And I think slab suction is another one of those. You do not need to know that, but I'm just saying if you're interested, there are others and you are free to Google them. Okay, here's a point question. If new crust is generated at a divergent plate boundary, so I'm going to bring up that picture one more time and erase all of this because it's getting kind of messy. New crust is formed at a divergent plate boundary because this magma solidifies into crust. And if these get pushed apart through seafloor spreading, where does this crust actually go? You can't just create an infinite number of crusts that take up the entire planet. It just doesn't have room. So these plates have to essentially go somewhere. Okay, and we're going to talk, the answer is convergent plate boundaries. So there are three types of convergent plate boundaries that we need to understand. When this crust moves apart in different directions, it is actually going to bump into another plate. So these would be two examples of divergent plate boundaries, and they occur all over the Earth. And maybe two of them are going to get stuck together, and they're going to have a little wrestling match. And we're going to talk about the result and who gets pinned under the other one. There are three types of convergent plate boundaries. This makes sense considering there are only oceanic and continental types of plates. If two oceanic plates come together, whichever one is more dense, it's usually the older one. The older one kind of just solidifies and grows old. That one's going to be more dense, and it's going to go underneath in a subduction zone. It's called a subduction zone, the plate that goes under. Okay, so this is an example of an oceanic to oceanic, and you can see that this plate is more dense, so it is going underneath. Now, you notice that this plate that's going underneath essentially gets recycled, and that's kind of cool, actually. So it gets recycled because all this magma and new plates form. It's a cycle. It's a cycle, ladies and gentlemen. So divergent plate boundaries create new crust. Convergent plate boundaries, one of them in a subduction zone, essentially goes to the magma to get completely destroyed. Okay, now because this is going all the way to the bottom of the ocean, it is going to push on a really, really deep part of the ocean called a trench. So that is how a trench forms, because this subducting plate is going to go under and essentially kind of make a hole or a space in the bottom of the ocean. Okay, so that's an oceanic trench, and it makes it to the the mantle, where it's essentially destroyed by all that heat. It essentially melts, but when it melts, some of that magma kind of seeps through and goes up to the surface. Okay, this is called partial melting, and it basically causes, in this case, in the case of an oceanic to oceanic, it causes a volcanic, obviously because of the magma, volcanic island arc. Volcanic island arc. Take a look at this word island right here. Okay, imagine all of this is ocean. Okay, I just have pure ocean. One of these plates gets subducted under the other plate. Magma comes upward. All this magma cools and forms crust, where it forms an area that we know today as an island. Not all islands occur like this through subduction, but some of them do. Now, finally, kind of a upper level concept, but this subducting plate can actually push this land. So the idea behind this is, let's say that the subducting plate is moving at a rate that's faster than this plate. So remember, we have two plates, and they're kind of moving in opposite directions, or they're trying to move past each other, but straight on. If this plate moves faster, it's essentially kind of stretching this land and making it more thin. Okay, so that is forming a back arc basin. So it's kind of pushing it back, so it's a back arc basin. I'll label that right here. This is a back arc basin. And since this is a back arc basin, this is a fore arc basin. The way I remember it, I know it's really lame, but I like to think of this subducting plate right here as kind of like a ladder that you climb. And if a person's standing right here climbing this ladder, behind them in their back is the back arc basin, and right in front is the fore arc. So I don't know how lame that is. If you want to remember it like that, please feel free. An example of a back arc basin, or the process that kind of makes this, would be, I don't know, the Sea of Japan. Just an example if you want to look that up later. Okay, now this is just if two oceanic plates converge. Okay, remember that the denser one is going to get subducted, and it's generally the older one. If I have an oceanic and a continental plate coming together, which one do you think is going to go under? Which one is more dense, oceanic or continental? I'll give you a hint. This one has a density of about 4.0 grams per cubic centimeter, mainly made of basalt and gabbro. That's right, it's oceanic crust, it wins always. Since oceanic crust is denser, it will always go underneath continental crust. Let's take a look at this picture right here. The same thing kind of happens, only you have land right here instead of ocean. So whenever this subducting plate goes under and this magma seeps upward, you don't have an island, but you do have a volcanic arc. Okay, you just have a range of kind of volcanic spots, like in the Andes Mountains. So that would be an example. Okay, now I do want to make a connection between what I talked about in the last video, and that is the difference between passive and active continental margins. So let's go all the way back to this fun stuff. Remember, I said that this was an active continental margin because of the presence of a trench. And trenches get formed whenever two plates converge and the denser one goes underneath. Generally an oceanic to oceanic or an oceanic to continental. It really doesn't matter. Either one of those will work, and one plate goes underneath the other one. One plate goes underneath the other one, forming a trench. So I just want you to know that an active continental margin is because of this interplate activity. And I think I have some notes on inter versus intra, but inter means between. Okay, so two plates are coming together and this trench forms. So that's why it's really common at active continental margins. So if you see trenches or volcanoes or earthquakes, then you're probably going to assume that some plates are colliding. Right? So another example of an oceanic continental crust. Do I talk about it? No, I don't. I'll just go ahead and mention it right here. So the Peru-Chile Trench, the Peru-Chile Trench, sorry about that, is essentially when the Nazca Plate, which is oceanic, goes underneath the South American Plate. You don't have to write this down. I'm just putting it up here for reference. So this is a continental crust, this is an oceanic crust, oceanic goes underneath, and that forms a trench, which is the Peru-Chile Trench. I do want you to kind of know that one. If two continental plates converge, I want you to think about this kind of logically. One of them is probably going to try to go underneath the other one, but understand that continental crust is above, okay, its surface is above oceanic crust. Because of that, it will never ever go underneath, and it will never see the light of day of the mantle. Okay, that being said, you really don't have a lot of magma trying to shoot upward. Okay, because this continental crust isn't going to go downward into the mantle, and it's not going to allow any magma to seep upward. So what's going to end up happening is these continental plates are going to come together, and it's going to kind of crumple up. And it makes me think of like a piece of paper. If you push it together, so this is my paper, if I push it together like this, it just kind of crumples upward. And that upward crumpling is the term for a mountain range in tectonics. Okay, so this mountain range is formed when two continental plates come together. Example in Central Asia is the Himalayas. All right, so we talked about divergent as they move apart, convergent as they move together, and one normally goes underneath the other one unless it's two continental plates. Transform plate boundaries are where they slide against each other. And here's the idea. The mid-ocean ridge is an area where all these plates are moving back in different directions, but they're at different sections. So let's say I have a divergent plate boundary right here that moves these plates in these directions, okay, and it would move plates in these directions. Well, look at this area right here. This arrow and this arrow are essentially sliding against each other, and that's basically what a transform plate boundary is. Again, why does this happen? Because plates among these different spreading centers, like area number 1, area number 2, are pushed in directions that allow them to kind of slide against each other. The example that you should be familiar with is the San Andreas Fault. It's an area where these transform boundaries occur. Okay, there's not really too much more to transform. But do know that it's a lot of seismic activity right there. So that earthquake stuff we did all of last chapter, okay, that's going to come into play with transform plate boundaries because these plates are kind of sliding against each other, and that's going to break some fault lines, causing this release of energy that we know as an earthquake. Okay, last thing that really doesn't have to do too much with this interplate activity, but before I talk about that, there's a difference between intra and inter. Intra means within, prefix is within, and inter is between. That's why an interstate highway is between two states, obviously, and an intrastate is within one. So, interplate movement is where you have two plates that do something. They interact in some way, like a convergent boundary. Intra is something that happens within one plate, and that is what a hotspot is. So a hotspot is different than a volcanic island arc in that a hotspot is an area in the mantle that just decides to release something called a mantle plume, and that's a bunch of magma that just happens to rise upward. Okay, I don't really know why this is. Sorry. Nobody really knows. I can give you a bunch of theories, but the fact is we're not really sure yet. But this mantle plume is going to rise upward, and an island is going to kind of form. But notice that this is on a passive continental margin, which means you're not going to see plate boundaries in this region. Okay, plate boundaries are going to kind of be nearby, but this is not the site of two plates coming together and doing something. This is all within one plate. Okay, so this mantle is going to rise and it's going to form an island. And you can actually track the age of these islands, considering that these islands are going to move apart because of plate movement. So this plate might be doing something with this plate in that maybe, I don't know, maybe this plate's moving this way and this plate's moving that way. I don't know, but plate movement is going to move this entire thing in one direction. Well, I want you to think about where this was a little while ago, apparently 3.8 million years ago. 3.8 million years ago, this was back here, and a mantle plume rised, creating this. Well, it moved in this direction, so you have this series of chains of islands, kind of like how Hawaii is formed. So I wanted to specify that. So you have one region that a mantle plume just constantly comes upward at. Plate movement is going to move this plate in this direction. Okay, this plate shifts completely, and you're just going to have a chain of them. Okay, I can't really demonstrate, but this entire plate is going to kind of shift. Okay, so different areas are getting affected, and that's why you have a chain of islands right there. That's the end of my tectonics unit. I hope all of that was helpful. In the next few videos, I hope to do some things on volcanoes, but for right now, that was a lot to digest. Feel free to watch this and the previous video again as many times as you need. The link to the notes packet I uploaded is in the first video, the link description in the first video. So again, I hope that was helpful, and thanks for watching.